Hello engineers, welcome to the new video of the course, and in this particular video we are going to design this particular circuit onto the LTspice software, and then we are going to verify the gain that we got theoretically. So theoretically we got the gain as minus of 133.33, right? And this is how we should be able to get the output signal from this particular circuit. If we are providing 1 millivolt of signal to the input side, we should get a signal of 133 millivolts, and that should be inverted, right? It should be 180 degree inverted. Okay, it should be 180 degree out of phase, right, with respect to the input signal. So this is what our intention is to verify or to check from this particular circuit. So let's go over here and let's go step by step. So first thing that we need to put onto the LTspice software is this, that is M1 and M2. Okay, so M2 is your PMOS, right, and this is your NMOS. M1 is your NMOS. So let's go over here and let's first select MOSFET. So I'll just click on component and then I'll click on NMOS. Okay, now over here, if you see very clearly, there are NMOS, two MOSFETs, basically NMOS and NMOS4. Okay, now you might think which one should we prefer over here. So as of now I'll go with NMOS. We'll see what exactly we get over here as we move further and further. So I'll just select NMOS, I'll just click on OK, and I'll just put it somewhere over here. Okay, then for PMOS, you again need to click on the component and you just need to click on PMOS. Okay, again for PMOS there are two different PMOS and PMOS4, right? Okay, the difference between this PMOS and PMOS4 is that, you see, the body terminal, it is not connected to the source terminal, right? So that's the only difference. Similarly, you see the difference between NMOS and NMOS4 is that this particular substrate terminal, it is not connected to the source terminal. So that's the only difference. Okay, so I'll go with PMOS right now. Let's see what exactly happens, and I'll just place it somewhere over here. Okay, great. Now let's see the circuit further. You see VDD is connected to 1.8 volts. Okay, VDD is connected to 1.8 volts. Now what generally happens is that most of the students, they just click over here V, and then they directly connect this to PMOS, thinking that this is their again pause this video and try to think, thinking that this is the source terminal of PMOS. No, the source terminal is present over here. So let me just delete this particular wire, delete this particular connection. Okay, so this is your source terminal, and you just have a look over here. The source terminal of PMOS is connected to VDD. So you just need to move this particular part above and this one below. So how you are going to do that? So you just click over here and you just select this particular component, and then on your keyboard just press Ctrl E. Okay, and then Ctrl R 2 times. Okay, so you see this particular PMOS we are getting in this way, right? That means your source is coming above and drain is coming down, right? Again, what I told you, how to get PMOS in this way. Okay, such that source terminal of PMOS should point upwards and the drain terminal should point downwards. So for that you just need to press Ctrl E one time. Okay, I'll just write over here so that you should not get confused. One sec. Whenever you will refer my PDF, will be able to understand each and everything, and that's why I'm taking a lot of time to explain each and everything step by step, right? So you just need to press Ctrl E, Ctrl plus E one time. Okay, and after that you need to press Ctrl plus R 2 times. Okay, and thus you are able to obtain what? The PMOS structure, such that the source points upward, okay, and drain point downwards. Okay, as we got right now, downwards, as you got right now over here. Okay, so this is how we are able to obtain. What we need to do, we just need to connect it. Okay, and then we will verify it. One second, let me just move it little below this little above. Okay, and okay, so we need ground as well. So I'll select over here, this is the ground. You see, I'll just place it somewhere over here, and over here as well. Okay, and let me just zoom this out a bit. Yeah, this looks fine. And now let me just move this little above, because we need to put V in over here, right? If you see over here, we need to sorry, one sec, we just need to put our V in over here in between gate of M1 and ground, right? So I need to place V in over here, and for that I just need to move this M1 above. Okay, let me place it somewhere over here, the ground terminal, this one as well over here, and this one as well over here. Great. So, and now let me again place V in over here. Okay, and let me just move it little above the entire structure. Okay, this looks fine. Okay, and let me move it little below this one. See, I'm taking a little bit of time so that you should not miss any of the point. Okay, so that's why I'm taking a bit of time over here. Great. And we need one more voltage, that is Vbias, which we need to connect it to M2, right, to the gate terminal of M2. So again, I'll just click over here on V. Okay, I'll place it somewhere over here and I'll connect it to ground. Okay, I hope you are able to recollect the you guys are able to recollect the shortcut command for ground. You just need to press one sec, you just need to press G over here and you see ground symbol appears. Okay, now we just need to connect the terminals. Okay, and let me one sec move this guy somewhere to the right hand side, because we are will be getting V out from between those two MOSFETs, right? So let me just move it somewhere over here. Yeah, that looks fine. And this as well, put to the left side. Okay, great. So let's connect the terminals. Yeah, so from ground it goes to VDD, and from VDD it gets connected to this MOSFET, one sec, and from here it gets connected to ground once again, right? And this guy, the gate of PMOS, it is connected to the Vbias. Okay, so this is your Vbias, and the gate of this particular MOSFET, it is connected to this particular input voltage, right? Great. And over here you are taking output, right? So we need to connect one capacitor of 10 microfarad, okay, to get the output signal. So I'll just click on, I'll just press C over here on the keyboard, and you see a capacitor appears, and I'll just click over here and I'll just press Ctrl R. Okay, great. And the value of capacitor is 10 microfarad, so 10 mu f, that's it. And again we just need to connect it to some to one wire, something like this. Yeah, this looks absolutely fine. Okay, so we have designed the circuit. Now we just need to assign the values to all of these particular components that we have placed over here. So the voltage that we are feeding to this particular circuit, it is 1.8 volts, right? So you just need to right click over here and just type 1.8 volts. Okay, then the most important point again over here, the Vbias is 0.02 volts. I'll just finish this one, and then I'll come to that particular point. So this is 0.02 volts. Okay, and your input signal is of 1 millivolts peak, and let's say you consider the frequency as, let's say, maybe 1 kilohertz. Okay, because the question has not mentioned about the frequency, we'll consider this as 1 kilo ohms. Okay, so I'll be going with sinusoidal signal. DC offset, of course we require a DC offset. Why? You see over here, what is my VGS? It is 0.5 volts. Okay, get to source voltage. So this should be, I mean, the DC offset voltage is nothing but VGS1. Okay, in this case. Okay, so it should be 0.5 volts, and amplitude it is 1 millivolts, right? So I'll take it as 1 millivolts peak. Okay, and frequency 1 kilohertz. 1 kilohertz. That's it. Now the most important point that we need to focus upon is this, that is the lambda and the other parameters of the MOSFET, W by L and all. Okay, how we are going to insert this particular values? So for that you just need to right click over here. Okay, and you see over here we are unable to provide any values, that is for W, for L, right? So we need to take those model, that is for NMOS and PMOS. We need NMOS and PMOS model such that we will be able to place the values for W and L respectively. So for that what you need to do is that you just need to delete it. I had intentionally taken this particular symbols, right, this particular model, because I wanted to show you that you just right click over here and maybe any one of the component, and you see we are unable to provide the values for W and L respectively. Okay, so that's the drawback which we get when we go with the normal model, that is PMOS and NMOS, right? So it tells us that you need to go with the NMOS 4 and PMOS 4. So again I'll click on component, I'll click on NMOS first, NMOS 4, I'll click on OK, I'll place it somewhere over here. Okay, and then again I'll click on component, I'll click on PMOS 4, I'll click on OK. Okay, so you see what I mentioned. First of all you just need to press Ctrl E. Okay, after that you need to press Ctrl R 2 times, so Ctrl R1 and Ctrl R2, right? And then we just need to click somewhere over here. That's it. Okay, so I hope you all guys understood it. As I had mentioned, Ctrl E 1 time and Ctrl R 2 times. Okay, great. So now before going further, let me just connect the substrate terminal to the source, to the respective sources. For NMOS it will be over here. Okay, great. I hope you understood it. Now you just focus over here. The moment I right click on this M1, you see we are able to give certain values to L and M, right? Sorry, L and W. We are able to provide certain values. Okay, which was not the case when we just went with the normal PMOS device, right? Okay, normal PMOS and NMOS model. It is only possible for NMOS 4 and PMOS 4 model. Okay, just remember this particular point. Anyways, we'll focus on the length and width. In case of NMOS, it is how much? One sec. Let me again go to that particular part. For NMOS, my W by L ratio is 20 by 1. That means my W is 20, L is 1. Great. So my W is 20 and L is 1. Okay, I'll click on OK. And for PMOS, it is 1 by 10. So my W is 1 and L is 10. Okay, so my W is 1 and L is 10. I'll click on OK. Yeah. So now you see we have completed almost everything. Just the thing is that we are just left with what? We are just left with this particular value. That means how we are going to assign the values for threshold voltage, this lambda, right? How we are going to assign these values, and in fact Kp as well. Okay, so now you just try to recollect that how exactly we are going to embed all of these particular values into these two models. So those guys who have learned MOSFETs 1 and MOSFETs 2 from me, they know how we are going to embed this particular values in the respective models, that is values for Kp, lambda p, lambda n, VTHP and VTHN into the respective models. Okay, just pause this video and try to think how exactly we are going to embed that. Just try to recollect how we embedded it in the previous scenario when we were actually dealing with the common source, common gate and common drain amplifier. Okay, when we design all of those amplifiers, how we embedded all of these values over there. Alright, I believe that you all guys have tried your best. Now it's my turn to explain you, to show you how exactly we are going to embed that. For that, if you could remember, you just need to click over here, right click, and you just need to click on draft and click on spice directive as. Okay, you will get this kind of video. Else you can also go over here, one sec, yeah, on edit, and then you just click on spice directive and this similar kind of window will open, and then you just need to type over here dot model, the name of the model. So right now I'll go with this one, PMOS. So I'll write PMOS. Okay, PMOS, and again PMOS. Okay, and then in bracket I'll write the value, that is Kp is 200 micro, right? If you could remember, it was 200 microampere, right? Kp is 200 micro. VTH is 0.4 and this is again 0.4, right? So Kp is 200 micro, VTO is equivalent to, because you know in this LTspice we don't have privilege to write VTH or VTHP or VTHN. We strictly need to write VTO. Okay, the threshold voltage, it is referred as VTO, and that is equivalent to minus of 0.4, and lambda, one sec, lambda is how much it was, one sec, for P MOSFET it was 0.05, yeah, 0.05. So this is the lambda. You just need to click over here and I'll just place it somewhere over here. So dot model PMOS, okay, in bracket Kp is equals to 200 micro, VTO minus of 0.4 for PMOS, and lambda is 0.05, right? So what I'll do, I'll again just I'll just copy it, and then we need to put dot model statement for NMOS as well. So again I'll just right click over here, I'll go in draft and then select spice directive, and again I'll just paste this particular model, and instead of PMOS we just need to write NMOS over here instead of PMOS, right? So NMOS, and again over here NMOS, okay, and then Kp will remain same, VTO will be 0.4, not minus of 0.4, and lambda for NMOS it is I guess 0.1 or 2, 0.1, yeah, lambda of n is 0.1. so I'll just write 0. I'll just select 0.1 and I'll then click on OK. Great. Okay, so yeah, this is the dot model statement, and this is how we actually embedded the values for Kp, VTO and lambda over here. I hope you understood it. Okay, now I just need to give the name, or I just need to provide the name for this particular node and this one. Okay, so I'll just give the name as Vout over here, Vout. I'll click on OK and I'll just place it over here. Okay, similarly I'll again click on label net over here, and I'll just provide the name of this node as Vin. I'll click on OK and then I'll just put it somewhere over here. Okay, now we'll quickly run this particular circuit. For that you just need to click on simulate, run, and we'll be dealing transient analysis because we need to monitor the waveforms, right, that we are getting, the input and output waveform, where it is. Yeah, we should able to get this kind of waveform, right? For that we need to do the transient analysis. My stop time, let's say it should be 10 millisecond. Okay, my start time should be 0, and maximum step size probably 1 millisecond. Okay, I'll click on OK. I hope you know how to do transient analysis. We had already seen that in the previous video, what is transient analysis and all. Okay, so I'll add two planes over here. So you just need to click on, right click over here and select add plot pane. Okay, over here I'll be plotting my input signal, and over here I'll be plotting my output signal. So I'll click over here and I'll plot my input signal. So yeah, this is how the input signal is. Now you might see that this is 501 millivolts, this is 499 millivolts, and you might ask that we are actually providing 1 millivolts, right? In fact, the question is asking us to provide 1 millivolt of input signal. One sec, where it is. Yeah, you see the question is asking us to provide 1 millivolt of input signal, but we are providing 500 millivolts. No, it's not like that. This 500 or 0.5 volts, it represents the VGS of N-type MOSFET, right, which was 0.5, and we have kept, you see, 0.5, and we have kept the DC offset as, one sec, you see, we have kept, one sec, yeah, we have kept the DC offset as 0.5 volts. So this 500 represents 0.5 volts, so that is the DC voltage. So we just need to extract that particular DC voltage. For that we need to put V in minus of 0.5. okay, 0.5 is what? It is my VGS, right? And I'll click on enter, so we will get 1 millivolt. You see, we are getting 1 millivolt peak to peak signal. Sorry, peak to peak signal is 2 millivolts, and the peak signal is of 1 millivolt, which is what the question is asking us to provide, right? 1 millivolt peak, and you can clearly see we are providing 1 millivolt peak. And if in case if it is not visible, let me just zoom it out. Yeah, you see it is 1 millivolt, right? Now we need to check the output voltage. So for that you just need to click over here and you just click on Vout, and you see this is the output signal. the very first thing that we should notice is that the output signal, it is 180 degree phase shifted with respect to the input signal, right? That is, my output signal is inverted. So that is first thing that we notice. Secondly, we just need to check the voltage again. So it should be minus of 133. So let's say for this particular signal, if I'm checking the voltage over here for the input signal, let me just write a few things over here. Okay, one sec, let me go over here and let me just take one rough page so that we can jot down few of the things. Okay, so as of now I'll just focus on my input signal. Let me check, let me take some different color. V in, so V in is how much? You see, V in, it is approximately 1 millivolt, right? 999,999 point something millivolts, right? That accounts for 1 millivolt, right? Technically speaking, it accounts for 1 millivolt, right? So this is any which was 1 millivolt. You can clearly look over here. That is my amplitude, right? This particular part, it is 1 millivolt, right? So my input is what? My input is 1 millivolt, right? Now let's check the output signal, and for that I'll write over here, and output, that is V out, is equivalent to, let's check that. So for that, one sec, let me click on V out, and now you see it is, let me move it somewhere over here because we are dealing with this particular signal, right? This particular part, it is approximately 137 point something millivolts, right? Quite closer to what we want, not exactly 133 millivolt as we wanted, but quite closer to what we want, right? So my V out is how much? It is minus of 137.06 something millivolts, right? Approximately it is 003, not 06, 03, something like that. Okay, 03 millivolts. So it is approximately 133.03 millivolts. Okay, now if you try to find out the gain, AV, the gain AV is equivalent to V out by V in. Okay, my V out is how much? Minus of 137.03 millivolts, and my V in is 1 millivolt. So this millivolts will get cancelled, and we are left with what? Approximately minus of 137.03. Okay, so that is our gain which we got practically, right? Theoretically we are getting gain of what? Theoretically we are getting gain of 133.33, right? And we expected this, we expected this kind of signal, right, which will go from plus 133 millivolts to minus 133 millivolts, and the signal will be inverted. So one condition is being satisfied, that the signal is inverted. So this condition is being satisfied. In fact, the gain is also satisfied, 137 approximately, not exactly 133, but it is quite closer to what we want, right? And there are few reasons for it. We'll come to that particular reasons later on, so don't worry about that. So the most important thing is that we are able to achieve the gain which we wanted, that is approximately 133 millivolts, right? So this particular circuit is working absolutely fine. I hope this particular part is absolutely clear, guys. Okay, I hope this particular part is absolutely clear. Okay, now let me first erase each and everything over here. Yeah, everything is clear, everything is crystal clear. Now what will happen, if I just increase this particular bias voltage, just pause this video and try to think. Let's say if I one sec, let's say if I increase this bias voltage from, let me add one more slide over here. We'll try to understand few more things over here. Let's say by bias voltage, let's say Vbias, right now it is how much? It is 0.02 volts. Let's say if I increase Vbias, let's say if Vbias is increased by 0.01 volts. So let's say if Vbias is 0.03 volts, what exactly will happen? Just pause this video and try to think what kind of output you you are expecting to get over here, what kind of output you are expecting over here. Just pause this video and try to think. Okay. Alright, I believe that you all guys have tried your best. Now it's my turn. So let me just increase it by 1. So let's say 0.03 volts. Click on enter and then I'll run. Okay. So what I can say is that the upper part, it is fine. You see, it is approximately 137, 138 millivolts. But the lower part, it is clipped, right? We're not getting the signal which you wanted, rather it is getting clipped, right? The lower part, it is getting clipped. What can be the reason for that? Okay, what can be the reason for that? Just pause this video and try to think in your mind what can be the reason for that. So what I'll do, I'll just end this video over here. You take this as an assignment. Pause this video, try to think, just take a pen and paper, just try to think in your mind that what can be the reason that this particular signal is distorted, or rather the lower part of the output signal, it is getting clipped. What can be the reason for that? Just pause this video and try to think in your mind. Okay, so I'll just end this video over here, and in the next video we'll try to deduce few more important points in this circuit. Okay, so if you have any doubts, if you are facing any difficulties anywhere till now, make sure to ask those particular doubts into the communication section. I'll be happy to help you out there. So thank you for listening patiently. I'm ending this video over here. Thank you.